Okay, let me first announce that I had a couple of emails regarding the quiz, last quiz, and that's on me because once I started it, that's when I realized I had said no sequential circuits, and then it was a sequential circuit. So I haven't yet decided what I'm going to do about it, but suffice to say, it's not going to negatively affect your student grades, okay? So I might either do like an extra credit with that, or I might assign it as a take-home completion after later on. But it will not negatively affect your grades, okay? That's what I'm trying to let you know. Still, I had more confidence in my students. I thought you'd be able to solve it. Okay, all right. Let's recap. So today, what I want to do is a little bit of number systems, and then we'll do a circuit analysis problem for the ideal diode. Okay, it was one of the homework problems. So we looked at binary, we looked at decimal, and then we spoke a little bit about hexadecimal. So today, I just want to take the first 10, 15 minutes and go over hexadecimal number systems. Okay. So hexadecimal number systems were devised as a way to represent the binary numbers. Okay. Is everyone done? All right. So hexadecimal system was designed as a way to represent binary numbers with fewer characters and fewer digits. Okay. So hexadecimal goes from 0 through 9, which is decimal. And A through F, hexadecimal. Okay, so we go from 0 through 15, 16 possible states. Okay, at the machine language, at the machine level, we use 4 bits to represent each character. Okay, 4-bit is a nibble, 8 bits is a byte. Right? We say kilobits of memory, kilobytes of memory, megabytes of memory, gigabytes of memory. Right? And so 4 bits is a nibble, 8 bits is a byte. And it's easier to represent it using 16 characters rather than just 10. Okay, and I will explain how it works. It actually is easy to convert from hexadecimal to binary and binary to hexadecimal. If we wish to represent a 4-bit binary word, we can use one single character. So if we had 1 byte, meaning 8 bits, meaning 8 different lines and 8 wires, we can represent it with only 2 hexadecimal characters. And going from hexadecimal to binary is as easy as simply replacing that hexadecimal character with its 4-bit binary equivalent number. So hex to binary is simply replace with the 4-bit binary number. So I'll explain with an example. Let's say we have F3A 0.2 in hexadecimal. And we wish to convert this to binary. Okay. We simply take each digit of this hex number and represent it with its 4-digit binary number. F is represented with 1, 1, 1, 1. 3 is represented with 0, 0, 1, 1. A is 1, 0, 1, 0. And then 2 is 0, 0, 1, 0. So the binary equivalent of F3A.2 would be 1, 1, 1, 1, 0, 0, 1, 1, 1, 0, 1, 0, 0.0010. as straightforward as that. So F3A simply represents 1111 0011 1010. So the obvious advantage is implicit right here. You have 16, not 16. We have a 12-digit number, 12-digit binary number, meaning 12 wires, 12 gates, 12 bits, represented with only 3 characters. Okay. So when we are programming, when you're programming the machine language or assembly language programming, all we need to type in is F3A. You're not typing 1111 0011 1010 12 times or 12 numbers. F3A, that's it, done. This is still in use today. Not still. This is the language that the computers understand. And so we use it. 30 years ago, when I was a student, I learned how to program assembly language. We use this hexadecimal language. If you look at the color codes, nowadays they say, okay, we have 1 million colors and 1 billion colors in our displays. If you look at those codes, there's an RGB code, and there's also an hexadecimal code. You will see colors represented with FFFA0156 or something like that, like a 6-digit hex code. And that each 6-digit hex code represents a digital color palette. And so if you can look it up, hexadecimal color codes, right? RGB goes from 0 to 255. RGB goes from 0 to 255. So all black or all white is either 000, meaning red, green, blue is all 000, and white is 255, 255, 255. Similar to the hex code, 0000, all zeros or all FFFs. Okay, so it's still in use today. Going from binary to hex is the same. We simply take, we group each digit or each binary number character in groups of 4. So we create groups of 4 digits. Okay. So if our binary number is 1111 0110.1, this number converted to hexadecimal. Then we create groups of 4. If needed, to create a group of 4, if needed, we can add leading zeros or trailing zeros. So if it's after the decimal point, then we add trailing zeros. So we can get, this would be F, this would be 6, and then 1 would become 1000. If it's after the decimal point, we add trailing zeros. We add zeros after the decimal point. And so this one, actually I wrote it in the wrong place. F, A, and 2. 8, sorry, not 2, 8. So this number becomes FA 0.8. FA 0.8 to the base 16. No, base 16. Yes. So hexadecimal has a base of 16, decimal has a base of 10, and binary has a base of 2. Depends how many digits we can how many values we can represent in with that single digit. All right. So that is hex to binary and binary to hex. Yes. If you wouldn't go in the middle of the decimal point. No. So I think the question being asked is we begin with the decimal point and then we move left and right. Yeah, that's correct. Yes. We would look at the decimal point and then start grouping them 4 points towards the right, 4 points towards the left. Yeah. And if needed, we'll add zeros right at the front, right at the front or at the back end after the decimal points. You simply create groups of 4. Yes. Yes. Yep. As with any number system in decimal. Yeah. But let's say you're using a multimeter to measure some voltage, right? And you measure 43 point, your expected voltage or current, for instance, is supposed to be 13 milliamps. Instead of 13 milliamps, you see something like FA0 or F1.8. Number would be correct, but it's hexadecimal, wouldn't make sense, right? So we would convert the binary into decimal. So we use a different system known as BCD, binary coded decimal, which is something that we perform in lab 7. How many of you have already done lab 7? Did it work? 0 through 9? Or did you go 0 through F? Did it work? Worked? Okay. So binary coded decimal is similar to hexadecimal, except we want to represent the numbers in decimal, so you only count up to 9. So we go 0 through 9. So BCD is a numbering system that stands for binary coded decimal. In this number system, we simply take each decimal digit and represent it with its 4-bit binary equivalent, similar to the hexadecimal conversion. Four-bit binary. So example, if you had 93.2 in decimal, and we'd want to create the BCD equivalent number, we would simply take 9 is represented as 1001. 3 is represented as 0011, and 2 is represented as 0010. And that would be the binary coded decimal for 93.2. This is one of the most common examples is using this in calculators, keystrokes, keypads. If you press 9 in a calculator on a number pad, internally, it shows you a transition of 1001. So 4 wires, 4 transistors, and the value of the output of that circuit would be 5 volts, 0 volts, 0 volts, 5 volts. 1001. Does that make sense? You press 9 on the keypad or the number pad, that translates to 4 bits, 1001, 4 wires, 4 circuits. The first 2 would be 5 volts, the next 2 would be 0 volts, the fourth one would be 5 volts, as an example. That would be binary coded decimal. So in lab 7, we take our asynchronous counter from lab 6, and we feed the output of that counter into a BCD, binary coded decimal, and then BCD2 decimal converter. Okay. So we take the binary output, convert it into a 7-segment display decoder. And that's binary coded decimal. All right, any other questions? All good? Okay, then let me take you back to chapter 1. I'm gonna add a slide at the end. Oh, that shouldn't be. All right, let's add a page and let's draw this circuit. This was a homework problem based on the ideal diode analysis. Remember this problem? This was D1, D2, D3, and D4. All resistors were 1 kilo ohm. We'll name them R1, R2, R3. And then you had V in equal to 0 volts, 2 volts, 6 volts, or 10 volts. You were asked to analyze the circuit using the ideal diode model. Okay, ideal diode model. Do y'all remember this? All right, first thing is I'm going to take you to a recap of E201. Okay. When I was a student, I used to have a hard time trying to apply KVL or KCL in circuits where you had dual power supplies, like plus 10 volts and minus 10 volts. In circuits, it's far easier for us to simply take a node and mark it as like, okay, this is plus V, this is minus V, this is reference point ground. Because if you try to connect all of those points using wires, you will have a lot of crisscrossing wires in the entire circuit. So we simply, to represent the circuit with a simple schematic, we simply do, okay, plus 10, minus 10, plus 5, minus 5, ground, 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 ground. Okay, so it's not explicitly shown in there. So what I like to do is, and I still do it, is I represent everything in terms of the components. Okay, plus 10 volts is plus 10 volts is shown, meaning there's a reference point or there's a point in the circuit where that node is 10 volts above that 0 volt reference. Make sense? Minus 10 volts simply means that point is 10 volts below that same reference point. So if I draw out my reference point, and I say my reference point is here, and I'm going to show that reference point as ground. When it shows ground in a circuit, it doesn't mean that it's physically connected to ground. Okay, that simply means it's a reference point in the circuit. Right? You have your mobile devices with you. They are not physically connected to ground. But if I was to draw a circuit for that cell phone or the tablet or your laptop, I would mark that negative point of the power supply as ground. That simply means is the common reference point. So this is the common reference point. This is 0 volts. Make sense? Then I have my resistor R1. Resistor R1 is connected to plus 10 volts, meaning this point of R1 is connected to a power supply that has a value of 10 volts. And plus minus simply indicates which end is lower and which end is higher. Make sense? Right? And same thing with R2. R2 is connected to minus 10 simply looks like this. And this is the power supply we created, the dual power supply we created for our op amps. We take two power supplies, plus minus, plus minus. All we are doing is we're connecting the negative end of the first one, connecting it to the positive end of the second one. So you're pushing the second power supply below the first one. So we get dual power supplies, plus minus. That's all it is. And so I always like to draw the circuit out in this manner. Okay. All right. So once we have this, let's go back to our circuit and analyze for, let's say, 0 volts. Okay. So now V in is equal to 0 volts, meaning V in is also connected to ground. Right? V in, the node is connected to ground. Makes my job easy. Let me assume all diodes are on. Again, as a reminder, ideal diode analysis, there's only two possible options. Either the diode is on or the diode is off. If the diode is on, we check for the diode current. The diode current must be positive. If we assume diode is off, then we check for diode voltage. The diode voltage must be negative. So if I assume that all diodes are on, that means all are replaced with a short circuit. Okay, all are replaced with a short circuit. So the diodes are going to look like this. Right? It's just a diamond configuration. And that means that everything is one single node. I1 is coming from the top. I2 is leaving. I3 is also leaving. The four diodes that formed a diamond configuration is now a single dot. Okay. So if I redraw the circuit with this in mind, it should look something like this. Vn is equal to 0 volts, meaning that's connected to ground. And then I have That would be it. 10 volts, 10 volts, R1, R2, and R3. That's how my circuit would look for V in equal to 0 volts and my assumption that all diodes are on. Okay. So far, so good. All right. So now it becomes a simple case of applying Ohm's law. We have two separate loops. We can apply KVL around the loop, find and apply Ohm's law, find the current I1, and then find current I2. In this case, it's straightforward. R1 is in parallel with the top power supply. So 10 volts is applied directly to R1, right? They apply directly to R1. And then in the bottom loop, 10 volts is applied directly R2. And so I1, I can write I1 is 10 divided by 1000. That gives me 10 milliamps. I2 is also 10 milliamps. And if you look at R3, what do you see? R3 is connected to one loop, and at the bottom, it's connected to ground. Where else do we see ground? On the left, Vin is equal to 0. Effectively, R3 is connected here between these two nodes. R3 is in parallel with a short circuit. And because R3 is in parallel with a short circuit, it's effectively redundant. No current can flow through R3. So I3 is equal to 0. Take a pause while you think over that. Let me know if you have any questions. Does that make sense? Because of my assumption, all diodes are a short circuit. And because V in is equal to 0, I can say R3 is connected across those 2 points, meaning across a short circuit. R3 is effectively redundant. No current flows through R3. I3 is equal to 0. Now, I have value for I1. I have values for I2. I take this tiny dot. Remember, this dot is basically all diodes. You expand it because our job is to determine the diode voltages and diode currents. In this case, my assumption is that all diodes are on, so I need to find all diode currents. I need to find ID1, ID2, ID3, and ID4. Okay, so expand. And if I expand, I get this. I have I1 coming from the top, that's 10 milliamps. I have I2 leaving the bottom node, that's again 10 milliamps. This I3 is 0 milliamps, but I3 is also connected this way, meaning I3 also comes in like this into the node. And if I3 is coming into the node that way, that is also off. Diode currents must be in this direction because all diodes are pointing down. So ID1, ID2, ID3, and ID4. Okay. ID2 must be equal to ID4 because I3 is equal to 0. And because I3 coming from here on the left, hence ID1 is also equal to ID3. But because it's 0, ID1 and ID2 summed together should give me I1, and ID3 plus ID4 should give me I2. It should be 10 milliamps coming from the top and 10 milliamps leaving from the bottom. So all diode currents are positive. So if you apply KCL at both of these nodes, and determine all diode currents, the result would be that all are positive. And if they're all positive, that means my assumption is correct. Okay, my assumption is correct. Take a pause for about 30 seconds or so, and then we move on. We have about 16, 17 minutes left. Any questions? Yes. Mm-hmm. So then we'd have to check for voltage. So the question being asked is if we made a different assumption, meaning let's say some diodes are on and some diodes are off. So for the on diodes, we need to find the current. For the off diodes, we need to find the voltage. Okay. So if there's an off diode, that means the voltage, the diode voltage must be negative. If it turns out, so we can, and you can do that as practice. This is a very good circuit for student practice because there are four diodes. So there are 16 possible states. Okay, so if you want to practice for the final exam, this is a very good circuit. 16 possible states. Assume two diodes on, two diodes off, analyze the circuit. If you assumed a diode to be off, you need to check whether the diode voltage is negative. For V in equal to 0 volts, you would not obtain a negative voltage. You would obtain a positive voltage, which would mean that your assumption is incorrect for V in is equal to 0. Okay. For the next V in 2 volts, you can still apply the same analysis, and you will still obtain the right answer. But I will jump directly to 6 volts because 2 volts, 6 volts, and 10 volts, the circuit will be the same, but the results are different. And I will explain how and why. Okay. So if V in is 2 volts, 6 volts, or 10 volts, this is how the circuit should look. Okay. We have our standard circuit like this. I'm just going to copy this directly, and so that makes things easier for me. Now, keep this as is. R3 would still turn out to be parallel because I'll explain in a second. Okay, R3 still turns out in parallel with that branch in the middle because obviously it's connected on the right. And on the left, we are saying it's connected to ground, right? So it'll always be parallel to those nodes. Not parallel, sorry. It's always connected between those two nodes. So it's always going to be parallel no matter what's in that branch. If it's a short circuit between those two nodes, it's R3 still in parallel. If there's a voltage supply in parallel in that branch, then it's in parallel with R3. Okay. So that's V in. So this is the circuit configuration for V in equal to 2 volts, 6 volts, and 10 volts, right? V in is applied from the left, and V in is positive, meaning that point is 2 volts, 6 volts, or 10 volts above my ground, okay? Which is this point right there. And this dot represents the diamond. Okay? That dot or that node represents the diamond, okay? All right, so I'm going to go through this quickly. My assumption is that all diodes are on, okay? So initial assumption is assume all diodes on, and I'll go to quickly find I1 and I2. So if I apply KVL around the loop and apply Ohm's law, I1 can be written as, and this is 6 volts. So I1 is 10 minus 6 divided by 1000. Gives me 4 milliamps. I2 is 6 plus 10. Actually, it's 6 minus of minus 10 and divided by 1000. So I2 is 16 milliamps. And I3, because it's in parallel with the 6 volt source, is 6 divided by 1000. So it's 6 milliamps. Now, if we wish to apply KCL, we need to know what the power supply through V in is. And I'm going to call that as X. Okay, I'm going to call that as X. If I apply KCL at the node to find X, I would get X is coming in, I1 is coming in, I2 is leaving, and I3 is leaving. Let me pause for about half a minute while you catch up. Let me know if something doesn't make sense. Yes. Random variable. You can just choose I in Batman, Superman, whatever floats your boat. Doesn't really matter. I Batman would be a bit much to write, so X. But a better choice, I get your point though. A better choice would be IX, just to indicate that it's a current. IX or I in or IS would be a better choice. So X would be equal to I2 plus I3, which is 16 plus 6 minus I1, which is 4. Gives me 18. 18 milliamps. Okay. 18 milliamps. So now we have that dot, right? We expand that dot to find the diode currents. Again, our assumption is that all diodes are positive. I mean, all diodes are on. So all currents must be positive. So we have that dot. We are going to expand the dot into a diamond. And then we apply KCL at those 4 nodes to determine all 4 diode currents. And so expand, and I obtain, it's not a good drawing. I1 coming from the top, all diode currents pointing down. So ID1, ID2, ID3, and ID4. I2 coming down, I3 going in this direction, and this should be X or IX. Let's just change it. Let's make it IX. Okay, IX. All right, so if you apply KCL, these are the equations we would get. Okay. You have I1 equals ID1 plus ID2. You have IX equals ID3 minus ID1. So IX plus ID1 is equal to ID3. So ID3 minus ID1. Right? 2 currents coming in. IX plus ID1 equals ID3. Yeah. And then I3 equals 2 leaving. So ID2 is equal to ID4 plus I3. I3 is equal to ID2 minus ID4. And then I2 is equal to ID3 plus ID4. You solve these, and you will obtain 2 currents positive and 2 currents negative. Okay. So you solve these. We're running out of time, so I'm going to jump through. Wait for a few more seconds while you get caught up. Okay. So again, solve these equations, find the 4 diode currents. It will turn out that ID1 and ID4 are negative. So do this outside of class as practice. And if it's negative, that means the diodes are not on and our assumption is incorrect. So if our assumption is incorrect, we need to go back and choose one of the other 15 possible combinations. There are 15 different analyses you can do with 4 different voltages, 60 possible problems. By the time you get through all 60 of these, 60, you should be able to handle any circuit that appears in the final exam. Sounds good, right? Good practice. Okay. What seems like the most logical assumption to make out of those 15? There are 4 diodes, D1, D2, D3, D4. We obtained 2 currents positive, 2 currents negative. What makes the most sense as the next assumption? That's possible, yes. So all diodes off is a possible choice. We can do that. And that, I will tell you, is very easy, because if all diodes are off, it's an open circuit at that node. It results in 2 separate circuits, and it's very easy. Boom, done. but you need to then apply KVL and calculate the voltages. Okay. But the most logical sense would be to take the two diode currents that we received as positive, we would assume those two on, and the ones that we obtain negative current, we would assume those two off. So in this case, if D1 and D4 is, not saying that it would be correct, but that just seems the most reasonable choice to make. So if D1 and D4 are negative, my next step would be to assume that D1 and D4 are off and D2 and D3 are on. I have about 3 minutes left, so I'm going to breeze through this. If you have to leave at 2, you can do so. All right, so D1 and D4 are off, D1 and D2 and D3 are on. It will result in a circuit that looks like this. On, this is D2, this is D1, this is D4, and this is D3. Plus minus, this is V in, this is 10 volts, this is 10 volts, and this of course is ground. And what this has done is that it has created two separate loops. When you apply KVL and solve these loops, you'll obtain positive voltage. And now you have to solve for VD1. Actually, you can solve for all diode currents and all diode voltages. Okay. The diodes which we assume to be on must have a positive current. And the diodes which we assume to be off must have negative voltage. And if you do that, then your assumption is correct. Finding the diode voltage would seem rather straightforward. You simply have one single loop. R1, R3, and 10 volts will form one single loop, right? Because this is connected here. That's one loop. And then 10 volts V in and R2 form the other loop. Finding the current through there is straightforward. Once you have that, calculate the voltage across the resistor, find the node voltages at the 4 nodes of the diode circuit. Again, if you are preparing for the final exam, this is an excellent circuit to use. You can solve this for 2 volts, solve this for 5 volts, solve it for, let's see. V in equal to 2 volts, 5 volts, 6 volts I've already done. You can do it for 8 volts. It will turn out to be very similar. 10 volts. Yes. Yes. Yep. 2 raised to n possible states. N is the number of diodes. N is 4, so 16 possible combinations. Plus, you can use V in as 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And 10 different voltages or 11 different voltages, 16 possible, 11 times 16 possibilities. But I will tell you, once it goes above 5 volts, the diodes D1 and D3 turn off. I mean, D1 and D4 turn off. So this assumption is correct. So I'm letting you know in advance. All right, so we'll end class here today. I'll see you all on Friday. We'll do more. Going forward, again, we'll do more problems. So we'll do more kind of like an open office kind of session where we'll just look at problems. If you have any questions, bring it up. If there's any problem or question that you had a concern about, you can bring that up, right? So we'll look at that going forward classes. Course content done. Yep. We can cover a bit more if you want to look at new material. I'd be happy to do so. Logic gates, logic design I have a lot of fun with that. We have barely skimmed the surface, which is what we're supposed to do in this class, though, skim the surface. Snorkeling, not scuba diving. All right, we'll see you all on Friday.